All right, let's continue. So, Shalin, whenever you're ready.
Okay, thanks for having me. So I'm going to talk about an operator formulation of Strassen's law, and this is joint work with Lin. Okay. So the law of the iterated logarithm is a statement for Brownian motion. So if you let BT be a standard Brownian motion, then the law of the iterated logarithm tells you that the lim sup as t approaches 0 of bt over square root of 2t log of 1 over t is almost surely equal to 1. Okay, and it tells us that although so bt has the same distribution as t to the 1/2 times b1, for each fixed t. So in particular, if you take the LP norm, the p norm of bt, it grows like t to the 1/2. So you expect some kind of t to the 1/2 envelope. And the law of the iterated logarithm tells you that the sort of pathwise excursions above that envelope are a little bit higher, and it tells you the factor by which they're higher. Okay. Now, Strassen's law is an improvement of the law of the iterated logarithm into a functional version. Okay. So it says that if you let b epsilon of t equal epsilon to the minus 1/2 times b of epsilon t, then with probability 1, the set of limit points of the random sequence b epsilon over square root of 2 log 1 over epsilon is equal to the deterministic compact subset of functions such that the L2 norm of the derivative of that function is less than or equal to 1. Okay? And that's limit points with respect to the topology of uniform conversions. Okay, so note that you can recover the original law of the iterated logarithm, because if you evaluate those functions at t equals 1, then the sup over all functions in that class k is equal to 1. Okay, and you can prove that using Holder's inequality. Okay, so our goal was to try to prove a version for Strassen's law for some SPDEs that arise naturally as scaling limits of random growth models and interacting particle systems. For example, the additive noise stochastic heat equation. Okay, so this is a stochastic partial differential equation driven by Gaussian space-time white noise. So that's just a delta correlated Gaussian field in both space and time. And it has a smoothing mechanism, and then it has a noise mechanism. And this equation describes things such as scaling limits of non-interacting random walks, scaling limits of the symmetric simple exclusion process. So various types of particle systems and growth models coming from physics. Okay, and another equation we want to prove Strassen's law for is the Kpz equation. So that describes growth models coming from physics which have an inherent asymmetry that sort of tries to propagate the growth in a lateral direction upwards. Okay, and I'll talk about that a little bit later. But first, I'm gonna focus on the easier equation. That's the symmetric. That is the additive noise stochastic heat equation, also called the Edwards-Wilkinson fixed point. Okay. So for instance, if you look at that first equation with 0 initial data, okay, that is invariant in law under the transformation where you scale time by epsilon squared, where you scale space by epsilon, and you scale the fluctuations by epsilon to the 1/2, okay? So based on the Strassen's law for Brownian motion, you might expect that if you normalize this process by some factor, then you can get a deterministic compact limit set in the space of continuous functions on space and time as epsilon tends to 0, okay? So it turns out that the correct factor, again, turns out to be log of 1 over epsilon square root, just like for Brownian motion. And so there's a general principle for this. take any abstract Wiener space. So due to time constraints, I haven't defined precisely what that is, but X is a separable Banach space, any separable Banach space. Mu is a Gaussian measure on that Banach space, meaning that if you push forward mu by any continuous linear functional in the dual space, then you get a Gaussian measure on the real line, okay? And H is the reproducing kernel, so H is the Cameron-Martin space of the measure associated to the measure mu, okay? So this is some compactly embedded Hilbert space in X that captures the covariant structure of the measure mu. One way to think about H is if you sample a random variable from mu, multiply that by square root of epsilon, then you have a large deviation principle with rate epsilon, where the rate function is given by 1/2 times the norm of H squared, okay? So the general result says the following, okay? So it says that if you take any collection of measure preserving bounded linear operators from the space X to itself, parameterized by epsilon from 0 to 1, and they satisfy a few conditions. So the operator norm of R epsilon is the operator from X to X, should be bounded above by epsilon to the minus some large number. Furthermore, if you take R epsilon X minus X, that should converge to 0 with respect to the topology of X as epsilon approaches 1. And furthermore, R epsilon, R delta, when you compose those, you should get R epsilon times delta, okay? So 1 and 2 can be more succinctly summarized as assuming that R of e to the minus t is a strongly continuous semigroup on the space X, okay? And the third and more fundamental condition in all of this is that R epsilon X, when you take the inner product with Y for any two vectors X and Y in H, that converges to 0 as epsilon tends to 0. So first of all, you might notice that I haven't even assumed that R epsilon maps H to itself, but that is actually an automatic fact that if you have any bounded measure preserving linear operator on X, then it necessarily maps H boundedly to itself. So assuming all of these conditions, the statement is that for almost every X in the space X, the set of limit points as epsilon tends to 0 of the sequence 2 log 1 over epsilon to the minus 1/2 times R epsilon of X equals the compact set K, which is the unit ball of the reproducing kernel, okay? So it's a little bit abstract, so let me talk about a few concrete examples. The first example is just Brownian motion. You can take X to be the space of continuous functions, H to be the reproducing, H to be the space of functions with square integrable derivative, and mu is Wiener measure. You set R epsilon F of X to be this thing, and you automatically, recover Strassen's law. Okay, I mean it's very easy to check all of those conditions. Another example is the one we wanted to do earlier, which is the additive noise stochastic heat equation. So that can be viewed as a Gaussian measure on any compact box in space-time. I just took 0, 1 squared for some reason. And then it turns out that the reproducing kernel of that is functions that have the same initial data that you impose on the equation, and such that the partial derivative in t minus the square minus the Laplacian in f, but the L2 norm is less than or equal to 1. Why? Because of the structure of the equation. The equation was this thing minus this thing equals white noise. White noise has an L2 reproducing kernel structure. So you obtain Strassen's law where you get the unit ball with respect to that norm. Okay. I don't have time for the remark, but you can actually, what I stated can be put into the context of various other results dating back to the 80s and 90s. What I want to talk about, though, is the Kpz equation. The Kpz equation is like the additive noise stochastic heat equation, but there's this nonlinear term that makes the equation ill-posed, okay? And that is a really problematic term. And so this thing does not have a solution in any classical sense. You have to solve it by exponentiating h, which then solves a linear equation, and that is called the Hopf-Kohl transform. So for the Kpz equation, you can actually prove that if you apply the same scaling as for the additive noise stochastic heat equation, and as epsilon approaches 0, you obtain the same limiting compact set as for the additive noise stochastic heat equation. Why is this? Well, it turns out that the solution of this equation is actually just a solution of the linearized thing, plus some remainder term, which is more regular than the solution of the underlying linear equation. And so that thing does not make a contribution when you normalize like this, okay? And so you can prove this in various ways. You can use chaos series, you can use theories like regularity structures or para-controlled calculus to try to control the remainder term and prove this statement. So one thing I want to note is that in this law of the iterated logarithm for the Kpz equation, you do not obtain any nonlinear behavior in the sort of small time regime, which is what you expect. But a sort of question that pops up naturally is there a way to scale the equation so as to obtain a nonlinear compact set in the limit? For instance, a set that reflects the structure of the equation, right? So the Kpz equation is this minus, sorry, this should be an F equals space-time white noise. Space-time white noise has an L2 structure. So it turns out that the answer is yes, but you have to scale the nonlinearity with some epsilon dependent factor while simultaneously scaling the space-time fluctuations, okay? So specifically, you should consider the solution of this equation, the Kpz equation, with this extra factor here for a fixed realization of the noise, and then consider the limit of this sequence where the epsilon appears in the superscript to reflect the fact that the equation parameters now depend on epsilon. And why is this? Well, the reason is because if you look at if you define capital H epsilon to be this thing, that solves this equation where the noise is now replaced by a rescaled version of the noise, okay? And based on our previous theorem, the set of all limit points of this sequence is equal to the unit ball of the reproducing kernel of the space-time white noise. And so if the map that sends the noise to capital H was continuous, then you would automatically obtain Strassen's law. So the main difficulty in what we want to do is that the map that sends the noise to the solution of this equation is not continuous. And again, it's not continuous because you need to renormalize, because this equation is very ill-posed and you have to subtract a large negative constant to make sense of this square, okay? And so you need more machinery to prove this sort of nonlinear Strassen's law for these type of equations. So again, we wanted to do this in some abstract formulation that would be applicable to other equations as well. And so we needed to formulate a version of our previous result with higher Gaussian chaoses. So if you let X H mu be an abstract Wiener space, the kth homogeneous chaos is defined to be the closure in L2 of the linear span of HK composed with F, where F ranges through all functionals in the dual space, and HK is the kth Hermite polynomial, which is defined here. Okay, so these polynomials orthogonalize L2 of the Gauss space, and a measurable map from that underlying Banach space to another Banach space is called the homogeneous chaos of order K. If you compose it with any linear functional in the dual space of the codomain, then you get something in the kth homogeneous chaos, okay? So examples would be Gaussian variables themselves. They're homogeneous of order 1, k-fold iterated stochastic integrals against Brownian motions. They are homogeneous of order k, square of the GFF. That's something that appears in Dinkin's isomorphism theorem. That's homogeneous of order 2. So the main result for higher chaos is that if you define psi hom to be this, then you let R epsilon and Q epsilon be strongly continuous semigroups on X and Y, satisfying some commutation relation, then you can actually prove a version of Strassen's law for the higher chaos. I guess I've kind of run out of time. So the fact is, you really only need to assume that there exists some R epsilon satisfying this, and you get the sort of behavior you want for higher chaos. I had an example. There's no time to do the example. But the point is that the Kpz equation still does not fall directly into that framework, but for equations that satisfy the local subcriticality assumption, there are theories that tell you that there's a factorization of the solution map that lifts the noise to some higher chaoses. And then there's a continuous map from that lift to the solution. So you can actually, sort of get that Kpz equation to fall within this framework after pushing forward by continuous maps. And
Okay,
so the references
great.
are the sort of classical results that were related to the first chaos. And here are the more recent things that sort of motivated this result in the, for singular SPDEs, more recent developments. And yeah, thanks.
All right, thank you very much, Shalin.